Hello, my name is Eric Kluwer. I'm going to start a channel, just going to chat about everything that I do. I've done a few projects, but never really recorded any of them. This is the project I've been working on for a while now, for about a year. And essentially, it's everything that's up here. I can get my marker. And up here, well, this is some of the math that I've done with it. And I'll just move this camera a little bit so that you can see better. Kind of move it with me. Keep things from falling. And I'll move it. Great. So, essentially what this is doing is, this is the fan laws. So I have these rotors. Let me get one real quick. This is another project, kind of like thinking ahead. What this one is this one's printed in castable resin. This Sierra, I can't pronounce it very well, but it's Sierra Tech, however you pronounce that. And this stuff, it will, you can put it in some plaster and put it in a kiln and cook it out. And the reviews there are good reviews about this stuff. And essentially, so it'll burn out and you can put metal in it, liquid metal, and have a perfect cast. So they say. The reviews are good, so I wanted to try it out. So I printed these rotors. This is a 115% scale of the ones that actually go in this tester. But that's just so I can get the wall thicknesses of the rotor thicker to make sure it prints right. And so yeah, that's another project. However, kind of thinking ahead, because whenever I build a jet engine, I'm going to have to make parts out of metals, which I'm thinking the compressor out of aluminum and the turbine out of aluminum bronze. But going off a little off topic, this up here is the fan laws. There are 3 that I found, and using 2 of them, where the V out is proportional with RPM and the power in is a function of RPM cubed. So what I do is I know, since from the fan law, since it's a function, I can put a constant that'll scale it up. And what that'll do is give me an equation where I can measure that constant, and that's based on all the geometries, everything that I have no idea is going to affect it. Don't know anything about that yet. What I want to do eventually is use my data that I collect here with this machine to come up with an equation that will reflect that and kind of predict what the rotors will do. But that's later. And since the velocity is proportional with RPM, I used Y as the scalar factor for that equation too. And plugging these into each other, the way I did it was I used flow rate. So I know the flow rate will be, it's rho AV. We're going to assume incompressible flow here. I got some books over there that'll give me the table, but this is like a 0.20% of compressibility at these speeds, because these speeds are like 5 meters per second. So pretty incompressible. But so I used flow rate to make the equation using the V out in power in and my scalar factors. And essentially that's all I've done. I've done some other stuff. Well, I have done other stuff in paper, but this is just what I have up here because I have very limited whiteboard space. I'll actually post the schematic for this project up here beside me while I go get the folder that I have all this in. And the folder essentially just tells, it's derived through thermodynamics, and it's essentially the change in enthalpy and change in kinetic energy across the rotor. And using that, I can derive the, in order to measure those two things, I need the initial pressure and temperature, initial velocity, and final temperature, velocity, and pressure after the rotor. And that'll get me the change in total energy across the rotor. So in order to calculate the efficiency, I need to also measure the power going into the brushless motor and then estimate the efficiency of that motor. They're about 90% efficient based on what I read online, the brushless motors. And so my equation, I just put it up here. And I used lambda as the efficiency variable. It's the flow rate times the change in enthalpy plus half the mass flow rate times the change in velocity squared, which that's just power of kinetic energy and power of enthalpy, over the electrical power going to the brushless motor over 1,000, because it's going from watts to kilowatts, times the kappa, which is my brushless motor's efficiency, minus the power of friction. So that's essentially what I'm getting. Just a little bit of math. And so the way I'm going to simplify this equation is by turning on the brushless motor without a rotor and run it all the way through up its RPMs with the different pressures and temperatures and velocities that I can do with the initial conditions. And I can make me a matrix that will have the initial power go into the brushless motor. Sorry, I have people who are closing doors over there. But initially, I can make me a table. So that will count for friction, and the inefficiency of the motor. And so what I can then do is put any rotor onto the machine and then subtract the two. The power that I'm getting with the rotor minus the power I'm getting without the rotor at the same RPMs and other conditions will get me the power going into the rotor itself, because that's all I care about. I want to eliminate all other factors other than that rotor. And then I can now cancel out the F times L over T term, and I can cancel out the efficiency term because it's already counted for. And this is essentially what this whole machine will do. It's been a lot of work to get the sensors to work, to get to 3D print, design and 3D print the module, the cone, and a climate control. It's been a year of work. So essentially that's this entire project, which I'm going to move the camera and let you see the project. Alright, so what we basically have here is pressure, so a BMP 390 sensor before the rotor and after the rotor, which will measure pressure and temperature. However, the temperature here is half a degree C accurate. So I want more accuracy, even though the enthalpy change across this rotor, I don't expect it to change much. The pressure and temperature of the fluid, the change from the rotor is not going to be much. So I may be able to detect something, I have no idea yet. But just in case, I bought these little TMP 117 temperature sensors, which are down to 1/10 of a degree C in accuracy. Also, I have my brushless motor inside this module. This is the 3 prongs for it. I have a pivot tube that goes down to a differential pressure sensor, and I have a gearbox. Some people may be asking why I have a gearbox for my Hall effect sensor. Well, the answer is that my brushless motor spins at 50,000 RPM. The fact that it spins at 50,000 RPM means that my Hall effect sensor cannot measure the RPM. It can measure up to about 6,000. So what I did was I have a bevel gear, a right angle bevel gear, which is a 1-to-1 ratio, and then I have 1 to 3 stacked on each other. So I have a total of 1 to 9. That means that 6 times 9, I can effectively read up to 54,000 RPM with this. And so I got around the fact that it's limited by the speed that this can be cycled. Also, I have a mass flow rate sensor. This is just my first solution to measuring the velocity, but I wanted to upgrade to a pitted tube. The issue here is that the differential pressure sensor that I have is very inaccurate at these low speeds. So I'm going to have to upgrade to a more precise but smaller range differential pressure sensor. And I'm just going to keep this flow rate sensor because it's plus or minus 3%, which is pretty good for the setup that I have here. And I have 2 computer radiators. These are 80 by 80 millimeter on a liquid cooled system. So it has a aluminum water block, one on each side of the Pelter modules, and I have 5 40 by 40 millimeter Pelter modules. And so they're 15 amps, 12 volts each. I have over a kilowatt of heating capacity effectively on here. And I have behind here a much bigger computer radiator to dissipate the heat. With the Pelter modules, the cool thing is that I can control it very well with the computer. I'm going to use a potometer, a digital pot, and a H-bridge. The H-bridge will switch the polarity so that I can cool and heat the box by just on demand, essentially. I can tell the computer I want to cool the box. I don't have to switch anything. The computer can control it. And the digital pot is going to be able to throttle the Pelter modules by lowering the current that are flowing through them. And so I can effectively maintain a very good controlled climate inside this chamber. And there's a lot more that I can go into detail with the electrical stuff, but this is just going to be a brief overview. The last thing is two last things. One of the things is I have this fan here. This fan, it's a big server fan that I'm going to use, and it's just going to be a closed loop. This is what the silver stuff is, a big PVC pipe with duct insulation around it. And so then this is about 12 meters per second speed coming off this fan. And so I have a 1 to 3.02 ratio diffuser here. And this is a 15-degree half angle, so 30-degree complete. And I could talk about the efficiency. I can't really remember offhand about the efficiency of this diffuser, the static recovery efficiency. However, that means that now I can take this speed and reduce it. That also, the reason I did that was because I need more precise control over the differential for the speed. I don't need very fast speeds. There isn't going to be very fast air coming off this rotor. I need very slow speeds with a very tight tolerance between each interval that I can throttle on this fan, because this fan has 0 to 255 input right on my code. So I have 255 intervals from 0 to full speed. And so this guy will give me more of a tighter differential in velocity as if I would have ran it without it. And the last thing I have is a compressor on this. And there's a lid that will go here, and it has 2 needle valves, so I can control the pressure inside pretty precisely. But one of them goes to a compressor so that I can pressurize this entire chamber. And that way I can actually change all the variables that I need in order to go from one stage to the other. I can put one rotor in here, run it at ambient conditions, get the data off of it, and then say I want to build a 4-stage compressor. Then I can take the final conditions off that first stage and make the ambient conditions in here those conditions. And thus, effectively, I can run the test again and call that the second stage. of the compressor. And that's pretty much it on this entire machine. However, I'm kind of looking at some more upgrades. I've kind of already thought about this and built it into the design. But there is, and I'll put it up like right here on the screen, there is two rotor, like a rotor and a stator. There's the thicknesses of the stator, and there's a gap in between the stator, well, the stator and rotor. There's thicknesses of both. And I'm going to keep them the same. So I can make, and I can also, so I have distances to move the stator and rotor against each other, and I can also make them thicker. So that gives me a little flexibility on some of the variables for the design of the rotor, not just the geometry, such as twist rate, the angle of attack, the number of blades, the chord width, which will be the thickness of the rotor, and so on. I found 11 different variables so far for the rotor themselves that I can go into this design. I've been talking for a while, so I'm kind of out of breath. However, that's pretty much it for this project. A lot of things that I've already started thinking ahead in the future about what I can do now to save me some headache later. But the main goal of this project was to better my understanding of the compressor, the axial compressor in a jet engine, so that I can better design one by experiment. And then I have an idea on how I can reverse this to where I can actually test the turbine for the jet engine as well. And that will allow me to mathematically build a jet engine without taking years to learn the math behind it. And that's pretty much it. I hope y'all thought that was interesting. I've been talking for a while. If you have any questions, just hit me up in the comments. And that's pretty much it. I've worked on this for about a year. I've done the mechanical, everything on here I've done by hand. I haven't outsourced anything. I've 3D printed everything myself. I've done the coding. I've done the electrical, the cutting for the wood frame that I have here, and everything. And I'm pretty excited to be almost done. Got done with most of the mechanical work today, and I gotta update the software, and I gotta rewire all the electrical stuff and improve the electrical stuff, because I have yet to improve everything. Everything's just functional. But yeah, I hope y'all have a good day.